Okay, I have a lot of things to talk to you as usual. Okay, so everyone pick up the team signature sheet and see, please put the dates on right away. And I have several handouts here. And this time I asked Michael to make only 24 copies, 25, because these are the these were the students who indicated that for Michael there's only section 8A. I thought that there should be.
That's also nice on the website. It was OB.
Should be ABC. Sorry?
That's all that was printed.
Yeah,
Only section 8A.
yeah, those three weren't up there today.
You know, I printed out ABC. Oh. So these are 25 copies. Yeah, they should be really ABC. Okay, maybe next time. So for those of you who need a hard copy, feel free to pick up. You know, and this is based on this survey in which 24 of you indicated that the hard copy lecture notes were used. Okay, so therefore I only ask Michael to make 25 copies. So please pick up those, and if there any extra, then help yourself. You know. Now the next item. Yeah. So sorry, this time for some reason I thought that I also printed out section 8B and 8C, but looks like there's only 8A. I have sent out an email about a new repository of solution guides on Sakai. So
AP and AC are in here.
oh, I see. Oh, so
AP and AC.
so let me thank you, Tony. Tony, notice that section 8B and 8C are also included in the handout. Okay. So you have A, B, and C all in the hard copy there, and there are some extra. So feel free to pick up if those who need it did not pick up. Okay, so we have a full set, ABC. Okay, and let's see. Let me show. So if you go into Sakai, and you go into the course and the assignment, I will put the link over here, you know, so you have the link in my email that you can go directly, because that's a Google Doc. And I will also put the link in the future in the home page of the Sakai site. If you go into assignment and you click at report 4, you also see the link to the solution guide right underneath the link to the report problems. Okay, so you can access the solution guide, and so it should be open. So in case that you see something like this, you know, it would be helpful if you have a Google account, then you have access to all of the reports in these Okay, in the future, I may think about putting a zip file. So Michael, so maybe we can zip all of these, and then also create a link here, so they can also download the zip file. Okay, so that should help. And once more, I'd like to mention that the best solution does not mean a perfect solution, right? There should be, there may be imperfection, that you need to use your best judgment or critical thinking, and not to copy without thinking or understanding. So here, I note here, use your knowledge to learn in the course, and your best judgment to decide which part of the best solution was not right, and exercise your critical thinking, or check with me before you check with me if necessary. And since after all, the exercise of critical thinking to distinguish what was wrong from what was right is learning, right? Is what learning is about. Okay, so please pay attention to that. And so yeah, fill out the feedback form so I can help. For example, some students mentioned that they knew which topic to learn but don't understand. Then please come to see me either in my office or through Skype. You can ask questions in class for active learning credits. Work with your teammates. Don't divide out the report problems. Okay, let me show here. Yeah, this is some that I noticed. Yeah, so right here, for example, there were 6 students who so far, right? So among the 22 respondents, I really hope to have more respondents. So please do fill out this form so I can address these issues. Yeah, so for these students, I'd like to invite to come to my office or talk to me on Skype. There are many ways. You can also ask questions in class, work with your teammates. Your teammates are additional instructors. In addition to me and Michael, the TA, some of your teammates are really excellent students, can really learn from them. And those excellent students also can learn by teaching, right? The best way to learn is to teach. So helping out your teammates is also the best way to learn. And don't divide out the report problems, because that way you don't have blind spots. Okay. So let me. Yes, that's one thing, and the other aspect is not enough written explanation. So I have already mentioned. My lecture notes is really extensive. You can also see me, talk to me via Skype, or if needed, I'll give you my cell phone number. I have the repository of solution guides. You can access through Sakai or through my email. And there's a lot of written explanations there. And so if there's still a problem, then see me. And this is to address, here in this concern, there's only one student, but I saw somewhere down, maybe lecture notes, perhaps. Yeah. If you feel that there's not enough, there are 6 students among 22. If you feel that there's not enough explanation, then there are several approaches that we could use as mentioned. Okay. Let's see what else. There's one thing that I just noticed. Yeah, the big picture. I hope that this issue had been resolved. I keep mentioning about the big picture a lot. So if you still don't see the big picture, again, come to see me and talk to me. Skype, cell phone, whatnot. Okay. Let me. So I think that should be sufficient there. And now I'd like to continue what we discussed last time, right? Recall that, and I have added some additional material there. Okay. Meeting 31. So here, okay, big picture again. You know, before we went into this, or unless someone wants to have an opportunity to remind the class. Of why we got into Taylor series. It's written that way. You know, this is part of the big picture. Okay, why did we have to do Taylor series? Anyone? Come on. Active learning credits. The bank. Anyone else? Anyone? Okay, so the bank. Go ahead.
We're using Taylor series because as of right now, we don't have any methods of solving the particular solution of law.
Yeah, so the bank sector. Hello. 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 Yeah, so the Van said that with the usual method in differential equation, you cannot solve problems that are excited by advanced function, right? So one method is to develop into Taylor series. Let me put on my microphone so that my voice would be louder. If you don't hear me from the back, please let me know, okay? And so this would is a reminder for this big picture that I was talking about. And let's see, it should be section 0B. Right, and I have already, yes, system right here. You know, for general excitation, actually there are three methods. One is Taylor series, and the other would be through projection, and this is a very powerful method. That includes the finite element method. You know, it is so advanced that I cannot explain it here. But trust me, projection is very, very important. And within projection, it covers two methods. One is power series, meaning how do you obtain power series out of projection, and the other is Fourier series. Let me, maybe I already organized it here. The first box is called the local method, because Taylor series, is only valid within a small interval around the point where you expand. I have an animation, but I need to look for it, and probably next time I'll show you the animation of log of 1 plus t. And the other method that is based on projection is called global approximation, because then you can approximate on a wider range. Okay, so keep in mind that Taylor series is really local in the sense that it will diverge from the function as you move away from the point. Okay, I promise to give you an animation. I just need to look for it. Okay, so here as an example of Taylor series, because in this note here, it could be really abstract to some student, when you just see formulas in general, but without a concrete example. And in fact, the concrete example is, why not expand logarithm of 1 plus t into Taylor series? And in fact, I did that. And in a note, okay, in fall 2013. So instead of rewriting the note, I would like to use my handwritten note. Let's see. I can click at the link. All of you can click at the link. But yeah, I think right here. But if I use this PDF viewer, I can zoom in, zoom out, and make it really more comfortable for everyone to read. Okay. And by the way, there's one more hard copy that Michael kindly made, and this is exactly a copy of my handwritten notes. Okay. Again, we made 25 copies, so there's still more here. For those of you who need a hard copy, and if there are any extra, feel free to have yourself, okay, even if you did not need a hard copy. So this way you can take a few notes, follow. Okay, so I'd like to move over this because I already wrote by hand, so I can move faster and therefore cover more material for you, because some students indicate, even though most students, the majority of the classes really find the pace was about right. Okay, I can show you the statistics. Okay, so let's take a very concrete example, log of 1 plus x. Yeah, feel free to pick up the hard copy. That way you can take a few notes. There's still more, feel free to do that. And we want to expand log of 1 plus x about the point x hat. Okay. X hat is the point that some student last time called A. Okay. If you expand into Taylor series in terms of x minus A, so x hat is A, if you like. Okay. And so this is the result where f with the superscript k in parentheses is the kth derivative of f evaluated at x hat. In reading through the team lecture summary, I noticed that actually some students did know this notation. I was really happy to see that. It's probably team 2. I'm not sure about the team number, but I did remember that some team did know this notation. Okay. Let me probably write this notation in my notes for today, so that you have that as well. Okay. Okay, so what I said is that f with k in parentheses x hat evaluated at a point x hat, and x hat is the reason that the hat was put on the variable x is to point to you that keep in mind that this is a fixed number. For example, x hat equal 10 or x hat equal to 0. Okay, it's not a variable. And the superscript k in parentheses simply means the following. Simply means that it's the kth derivative of f, and you evaluate the derivative at the point x hat. Okay, that's what that notation meant. Okay. Okay, so let's go back to my notes here. And so what I did is to proceed to derive this formula. Okay, this is the full expression for the Taylor series. And how I obtain that is just by successively differentiating. Okay, so let me show you just a few steps, and you can read and ask questions later if necessary. Yeah, so you know, f is log of 1 plus x, right? So the first derivative of log of 1 plus x is 1 over 1 plus x. Okay, and at this stage, maybe let me make the window a little bigger for the camera. When the window is small, it loses focus. Okay, so this is basically the derivative of log of 1 plus x, and therefore is 1 over 1 plus x. And when you evaluate the derivative at the point x hat, then you simply replace x by x hat. Okay, keep in mind x hat is equal to 0 if you like, or 10 or 15. It's just a fixed number. And now you define w to be 1 plus x. Okay, define w to be 1 plus x as shown there. Then w prime is 1, and the function w is an intermediate function that plays a role in subsequent derivation. So let's look at the second derivative. Okay, so now the second derivative, okay, because the first derivative can be written as 1 over w, so the second derivative is minus w prime over w squared, right, which is just derivative. There's nothing new there. But because w prime is equal to 1, as w is 1 plus x, so w prime is equal to 1, then you can replace the numerator by minus 1, and the denominator is still w squared. Okay, and then you move on to the third derivative. My third derivative is by taking the derivative of this fraction here. Okay, that's just carrying out and this fraction is minus 1 over w squared. So you have in the numerator, you have the minus 1 which came from here, and the derivative of this is 2w prime, and then you have another minus, and down here you have the square of w squared, so w to the power 4, right? And w prime is equal to 1, and w, yeah, so w cancel with w4, so that's w to the power 3, okay? And then you have minus 1 to the power 2, all right? So this is the result for the third derivative. Okay, and now let's move forward. Let me erase clear the ink. And then you keep on doing the fourth derivative, the fifth derivative. Okay, now let me move to the probably the fifth derivative. You see, be careful because you don't want to simplify certain things. Yeah, so therefore let me keep the fourth derivative and the fifth derivative together. You know, all of these numbers are very useful to obtain a general formula. For example, the fourth derivative is minus 1 to the power 3, 1 times 2 times 3 divided by w to the power 4. And the fifth derivative is minus of minus 1 to the power 3, 1 times 2 times 3 times 4. And then you have w to the power 5. You see, if you compare this formula to this formula, you see a certain structure that you can generalize. And that's very important. Okay. And that is so that the end result, let me leave w, the fifth derivative here, so that the end result is that you can write the kth derivative in a very compact formula. Okay, that is valid for any value of k. That's very general, right? So minus 1 k to the minus 1, k minus 1 factorial divided w divided by w to the power k. Let's check. If k equal to 5, right, then you have minus 1 to the power 5 minus 1, that's 4, right? And k minus 1 is 4. 4 factorial is 1 times 2 times 3 times 4. And down here, w to the power k, k is 5. So that's w to the power 5. So this same formula is valid for all orders of differentiation. Okay? And so that in the end, you obtain this compact formula that I showed at the, this one that I showed at the beginning. Okay, this is the result. This is the general result of the Taylor series, right? Taylor series of in fact, this formula here is the general Taylor series for any function f, and then when applied to log of 1 plus x, you get this result. Okay, so this formula down here is the Taylor series of log of 1 plus x. When you replace the expression for the kth derivative of f as evaluated at x hat, okay, into the general formula up here, then you obtain this formula. Okay. Notice x hat here and x minus x hat. That's what some students mentioned as x minus a. Okay. And a particular case is you can particularize to the case where x hat is equal to 0. So this is expanding Taylor series about 0.0, okay, not Taylor series. And so when you replace x hat as equal to 0, then this is a very compact expression of the Taylor series of log of 1 plus x, you know. And so with this formula, you can animate, you can create an animation. I really wish that I have the animation here, but I will look for it, okay, because I would like to instead of spending time looking up the animation, I can move forward. Okay, so please just keep in mind this very compact formula, and I will show you next time in the animation that you will observe the following. You observe that this series here would converge only on a finite interval, you know. So outside that interval, it would diverge from the function log of 1 plus x. So that's why the Taylor series expansion is called the local approximation method, because it can only approximate locally about the point x hat. And in this particular case, x hat is equal to 0. Okay. So with the animation, you will see more concrete picture. All right. Let me go back to this daily lecture summary here. So section 8, I'll ask you to watch the video, and there's a lecture notes there. And also section 8B, okay, 8A and 8B have my lecture videos that you can watch. Now let me run through just a quick run through of section 8A and 8B. And, I can close this one down now. Okay, so Fourier series, and the motivation is force oscillation, approximation by Fourier series. You can go through this. Everyone knows what's a periodic function since high school. Sine, cosine is an example. Now here it would be a more general periodic function. And so if you have a function that is periodic and excite a linear second order ODE, for example, well, it could be a multiple degrees of freedom system. So you have a system of second order ODEs, and you use the method that you learned in the first half of the semester to uncouple, right, into a series of uncoupled scalar second order equations. So that is known. That's going through eigenvalue problems and all that. So you are now all expert. And I hope through discussion with Michael and Casey that in the vibration course, this is only now that they get into multiple degrees of freedom system, and even then only the undamped free vibration. Whereas in the first half of the semester we treat the most general case where you have excitation and you have damping also. Okay, and the method that was taught, or that is being taught in that course, vibration, right now, is to transform a generalized eigenvalue problem into a standard eigenvalue problem following method 3. Okay, what I discussed, and they did not even discuss how to solve the generalized eigenvalue problem. Okay, so you know more than what is taught in the vibration course. Now, in the case where you excite the system by periodic function, and when you use eigenvalue problem to decompose into scalar eigenvalue problem, you would also have periodic excitation. And so the solution is essentially decompose if you have a sum of excitation, then because of linearity of the second order differential equation, you can do as if you excite the system by each of the summand, each of the term in the summation, right? So if this, let me open a new, a bigger window so you can all see much at ease. Yeah, so what I'm saying is the following. So if you have the excitation that looks like this, right, a summation of many different functions, then because of the linearity of the problem, you can decompose the system by exciting first with R1, right? When you excite with R1, you get a particular solution corresponding to R1. That's where I is equal to 1. And then you excite with R2, then you get the particular solution corresponding to R2, and then so on and so forth. And in the end, you can add all of the particular solutions with I going from 1 to n, and you get the particular solutions, right? And so that's the idea. And one way to, if you have a general function, you can decompose into Fourier series. So this is the Fourier series here, where you see what is a Fourier series. It's just the sum of many excitations, right? Just like what I showed in the general case, this can be thought of as R0, and then R1, R2 to infinity. In fact, the Fourier series is an infinite series. Now this term here has a very important meaning. It's really the average over a period. Okay. And in electrical engineering, this term here is called the DC component. DC stands for direct current, and that's basically the average. Okay, and then you can excite the system by each of these sine or cosine terms. If you excite by a sine or cosine term, you know the form of the particular solution that you should use. That in section 8a, you know, and also in differential equation. Okay, so please look at these so that I can provide more. So right here. Okay, so if you excite either with cosine or sine, then your particular solution has to contain both cosine and sine. Okay, just because the reason is because when you differentiate, the cosine will become a sine and the sine will become a cosine. And here you have to differentiate twice. So this is something that we need to keep in mind. Okay, and so let me see. Let me zoom out here for a big picture. And so this is called the Fourier basis. Okay, the Fourier basis consists of 1 and then cosine of n omega x. Maybe let me zoom in so that it's easier to see. And sine of omega x. Okay. With n going from 1 to infinity. N is the factor that is multiplied by omega here, and 1 can be thought of as cosine of 0, meaning n equal to 0. Okay. Whereas you don't want to have sine of 0, because sine of 0 is 0, and 0 is not a basis function that you want to use. Okay, so therefore we eliminate 0. And down here, what you see here is the polynomial basis. Okay, so polynomial basis consists of x to the power n, and with n going from 0 to infinity. With x to the power 0 is 1. So you see there's a commonality between the polynomial basis and the trigonometric or Fourier basis function in that the first basis function is 1. And 1 is very, very important. Okay, because without the basis function 1, you cannot have the average of the function represented. Okay, and so all of this is in section 8a. So please look through. Section 8b is a more. Oh, I have two sections. 8a, yeah. Let me look for section 8b. Section 8b presents a very general right here. method that includes Fourier series as a particular case, and that's projection. Okay, so let me bring up section 8b here, and so here projection, and so down here let me give you a big picture first, and then I'll talk about the details. Okay, first I bring you back to the case of vectors, but not that simple. It's much more than you think. Okay, you know since many years ago how to find the components of any given vector in a Cartesian coordinate system, right? Cartesian coordinates means that the two coordinate axes are orthogonal, and the unit vectors are of unit length. But okay, so first, why do I want to bring vectors? Okay, you may think that vectors is something that you have known, but here's a deeper reason, because we are going to deal with functions. And the powerful concept is that you can think of functions as vectors. Okay, so with vectors you can talk about the components, right? Projecting a vector onto a basis vectors, and you get the components. With function, the same thing, right? We use the terminology basis functions, right? So these functions form a basis, just like the basis of the vectors. Okay, and yeah, so what is more important here is how do you find the components of a vector when you have an oblique coordinate system. An oblique coordinate system is a non-Cartesian coordinate system, right? When you do not have 90-degree angle. Okay, so that's the concept, and let me immediately motivate you why. Okay, so with vectors, right, you have two types of bases. The Cartesian coordinate system, that's when the two coordinate axes are orthogonal to each other, and the oblique coordinate system, when the two coordinate systems are not orthogonal to each other. Let me look to see whether I have drawn the picture. I think I did. Let me leave it here and move over here. Okay, I think I did draw the picture, so that way I don't have to redraw the picture and we can move faster. Oh, no, I can redraw very quickly, easily. So here, okay, Cartesian coordinate system, everyone knows, no problem there. Let me just redraw just for the sake of recalling. So if you are given a vector v, you know how to project, thank you Casey, down to the coordinate axis and find the components, right? But if you are given an arbitrary coordinate system that is oblique, so that is represented by these two lines here, and given the same vector v, okay, how do you find the components of this same vector v relative to the oblique coordinate system, right? And that is something that you may do geometrically, as in statics, right? In statics, remember, if you have two forces and then you have forces here, you can draw a parallelogram. But that geometric method only applies for 2D, right? Number one. Number two, cannot be generalized to function. Okay? But keep in mind the two concepts, orthogonal basis and non-orthogonal basis. What is, before we finish, what is the equivalent in terms of functions? The equivalent in terms of function is written right here. Let me see. I think in this note here, I must have written Yeah. Just to give you a look ahead. The Fourier basis function is the equivalent of the Cartesian coordinate system. The functions are orthogonal to each other. Okay. Whereas the polynomial basis function is the equivalent of the oblique coordinate system, where the basis functions are not orthogonal to each other. And the question is, what does it mean expanding into Fourier series or expanding into power series? That's to find the components. Okay, that's to find the components of any given function relative to the basis functions. Okay, so one last word, Fourier series. Fourier series, the coefficients that you see here, right? The coefficient A0, AN, BN are the components of the function R relative to the basis 1 cosine n omega x and sine n omega x. Okay, that's your summary.
Yeah, so we got plenty of time. Because I was just wondering, can you send me that?
Yes.